Welcome to the massive open online course on Aspen Plus. In today's lecture, we will perform some practice problems on binary mixture. In the last lecture, we have done the practice problems on pure components. Today, we will do on binary mixtures. Altogether, we have 5 problems to solve. The first problem is about comparing the ideality of pentane-heptane mixture through analysis of TXY and XY diagrams. And we will use ideal and Peng-Robinson property methods. For that, let us go to the Aspen Plus simulation window. So here we have to first enter the components, which are pentane and heptane, and we shall use the ideal method as well as Peng-Robinson method. So let us run the property method. Yeah, the property methods are run. Now we have to bring in the binary mixture. So we brought the binary analysis tool. Here we have pentane and heptane. For pressure 1 atmosphere, the calculation option is Peng-Robinson. First, let us do with ideal method. We will do Peng-Robinson later. So for ideal method, if we run the analysis, we obtain this particular curve. Now let us change it to lines only. Do not use marker. And we write ideal because later we have to distinguish it from Peng-Robinson method. So binary plot is done. So now we will bring in another binary analysis, and in second binary analysis everything will remain same, only the calculation option will change. In the previous case, we did it with ideal property method, and this time we will do it with Peng-Robinson method. So let us run the analysis once again. So this is the TXY diagram for pentane and heptane when Peng-Robinson method is used. So here again, we use only lines, not markers. And we change it to Peng-Robinson and Peng-Robinson over here. So this is the diagram for Peng-Robinson method, and this is the diagram for ideal method. This is the diagram for ideal method, and this is the diagram for Peng-Robinson method. And let us merge the plot and check. Yeah, we have merged the plot, and we can take everything in the single axis. Okay. We find that the results obtained by using ideal method and results obtained using Peng-Robinson method, they almost match with each other. The curves, they superimpose on each other. The bubble point curve almost exactly match with each other, and there is slight difference in the dew point curve, but that is acceptable. So now let us check the XY diagram. So this is the XY diagram for Peng-Robinson method. And for binary 1, let us bring the y versus x curve. Yes, this is for ideal case. Okay, so we use only lines, and here also we use only lines. Okay, now we merge the plot. So here again we merge the axis. Yes, so we observe that for YX diagram, that is YX vapor liquid equilibrium diagram, the result obtained through ideal property method and the result obtained through the Peng-Robinson method, both of them, they almost superimpose on each other. The error is, or the difference is very, very minimum. So from this analysis, we can conclude that pentane-heptane binary system is nearly an ideal system. The non-ideality is very, very minimum. Now we go to the next problem. Here we have a water acetonitrile binary system at 1 atmosphere pressure. Now we have to do 3 tasks over here. There are 3 property methods suggested: NRTL, Peng-Robinson and Wilson. We have to check which is better suited. And this information we have to verify with the NIST data set. And we will expect that Peng-Robinson parameters will not be very good because water acetonitrile binary system at 1 atmosphere pressure will be mostly liquid. So activity coefficient model will be better suited. So for that matter, NRTL and Wilson method, they are expected to perform better, and Peng-Robinson method perhaps will not perform better. So we have to improve the Peng-Robinson parameters through regression so that its performance comes to an acceptable range. And then the third task is we have to check whether the change of pressure helps in separation of water acetonitrile azeotropes. Now here we will expect that the system will have an azeotrope, and if we need to perform distillation in order to separate water and acetonitrile, then changing pressure, whether it will help. So that we have to check, and for that task we have to use NRTL property method. So for that we have to go to Aspen simulation window and we will open a new simulation. So we enter the components. First is water, and then we will have acetonitrile. So this is the one which we are looking for. Add selected components. We rename it to acetonite. Next, So we have three property methods: inertial, Wilson, and Peng-Robinson. So these three methods we will operate. Okay. Now let us bring in some NIST data. So we have binary mixture for water and acetonitrile. Let us retrieve the data first. This may take a few minutes depending upon the speed of internet. Yeah, so we have got some binary VLE. Suppose we choose the first one. Yes. So it is VLE 001, the liquid mole fraction, water, and this is the temperature in Kelvin, and this is the vapor mole fraction of water, and this is the pressure. So pressure is 101,325 Newton per square meter. That means it is 1 atmosphere pressure. So let us save this data. Okay, so we'll go to the data set. Yes. Now this data type, as we have the pressure data, so Aspen is assuming that pressure is changing. So it is showing it as a TPXY data table. But we understand that pressure is constant at 1 atmosphere. So what we will do, we will change it to TXY in place of TPXY. In that case, we have to add some constant temperature or pressure data over here. So we will change it to TXY, and we will write over here 101,325. Now in the data set, the pressure column disappears. Now let us check the TXY diagram. So this is the TXY diagram we have. Right. So this is the experimental value of TXY data for water acetonitrile system. The blue dots are the vapor fractions, vapor mole fractions, and green data, green squares, they are of X, that is the mole fraction of water in the liquid. Okay. So both of them are mole fraction of water, not acetonitrile. Now what is the temperature range? The temperature range is 348 to 374. Now let us go to the binary analysis. For that, let us bring in binary analysis tool. This is the TXY diagram, and we keep it at 1.01325 bar because this is the pressure at which the experimental data has been obtained. So First we will do with NRTL. So run analysis. Okay, here we change it to lines only and change it to Kelvin because the experimental data are there in Kelvin. So if we have to compare it with experimental data, we have to change it with Kelvin. And here we write NRTL because later we have to distinguish it from others. Okay, so now we bring the second binary analysis tool, and here everything will remain same, only the calculation option will be different. It will be with Wilson rather than NRTL. So we run the analysis once again. So we get another result. We just keep the lines, not the marker. We change it to Kelvin, and then we write Wilson over here. Wilson, done. So we have got the TXY plot using NRTL method, and then we were using with Wilson method. And the third one, again, we will bring another binary analysis tool, and this time we shall use Peng-Robinson method. Run analysis. Okay, so visibly this curve is not acceptable. Okay, anyway, just change it to lines and then bring over here, write Peng-Robinson, Peng-Robinson again. Okay, done. So binary 2 plot, it is Wilson, and binary 1, it is NRTL. Okay, now we have to combine all these curves and check. So this curve, we merge the plot with binary. Binary 3 also we merge it binary 1, and the experimental data, that also we merge with binary 1. So actually the binary 1 curve, now it has 4 curves. So all of them we have only the lines, not the markers. And we shall change the axis to single axis. Now you can see the experimental curve, this one, we keep line and marker, or we can keep marker only, because this is the experimental curve. And then the other one, that is blue line, this one, we keep marker. Yes. So now we can see the experimental data and the TXY diagram obtained by using three property methods: NRTL, Wilson, and Peng-Robinson. So visibly we can see the two methods like NRTL and Wilson, they are able to come near the experimental data. Okay, they somehow are trying to match the experimental data, but the Peng-Robinson method, it fails miserably. Now it is expected, because Peng-Robinson method is equation of state method, not activity coefficient. But here we have the next task. We have to improve the Peng-Robinson parameters through regression. Now we have deleted all other things like NRTL and Wilson method, we have deleted. We have just retained the TXY diagram obtained through Peng-Robinson method, and that we are comparing with the actual experimental data obtained from NIST. And this is the result that we are getting. The solid lines, they represent the simulation result obtained through Peng-Robinson method, and the red dots are Y experimental mole fraction, and the magenta squares, they are experimental data for mole fraction of water in the mixture of water and acetonitrile. So this one we keep now for the time being, and we want to improve the Peng-Robinson method. So our next task is improve the Peng-Robinson parameters through regression, so that the improved Peng-Robinson method can match with the experimental data that we have got. For that we have to do the regression. So let us bring in the regression over here. So press new, the new ID, and the data set, we have only one data set over here, and the parameters. So first let us check the binary parameters, and we will choose PRKBV, that is the binary parameter vector for Peng-Robinson equation of state, the Kij. So let us use, it is first element, component water and acetonitrile, and let us run the regression. Okay, so it has run. Now let us run the binary analysis once again with the improved Peng-Robinson method. So this is the binary curve, and this is the result that we have got. Earlier, at least this portion was here. So actually the model got worse after regression. So we have only regressed one parameter. So that might be the reason. So the next time, what we will do, we will increase the number of parameters. Say we shall regress this one, and then we will regress this one and let us regress another one which is mu. Let us see whether we get a better result with them. So run the regression once again. So yes to all. So all of them have been changed now. And this is the updated curve. Yeah, now it is much better. Okay. The green and blue lines, they are model output simulation result through improved Peng-Robinson, and the dots and squares, they are experimental data. This result is much improved ones. So we can conclude that by changing 4 parameters, the Peng-Robinson method becomes better. So I believe that if you increase 1 more parameters or 2 parameters, then the result will be much better. Our next task is to check whether change of pressure helps in separation of acetonitrile azeotropes. We have to use inertial property method. Now if we check the curves, we will find at this point we have some azeotrope. Okay, so if my system has 27.5% of water and rest is acetonitrile, then we'll not be able to separate them through distillation because that combination forms an azeotrope. Now we have to check by changing the pressure of the system whether it helps. So for that we have to use inertial method that we have done. So we will use inertial method over here. Now whether or not change of pressure helps, we shall not analyze it with one pressure, rather we will analyze it with multiple pressures. So let us analyze it at 1 atmosphere pressure, 5 atmosphere pressure, 10 atmosphere pressure, and 25 atmosphere pressure. Let us check 4 pressures and see how the TXY diagram looks like. So run analysis. So this is the diagram that we have got. This one is 25 atmosphere pressure. This one is 10 atmosphere. This one is 5 atmosphere. And the last one is 1 atmosphere. So as you can see that as the pressure increases, the temperature also increases. So that is expected. Here one thing you can notice that at 1 atmosphere pressure, the azeotrope lies somewhere here. If we increase the pressure up to 5 atmosphere, then the azeotrope shifts. With 10 atmosphere, it further shifts, and with 25 atmosphere, it shifts again. So, if your binary mixture contains, say, 30% water and 70% acetonitrile, then obviously with this composition at 1 atmosphere, it is not possible for you to separate through distillation. But same thing is possible at 25 atmosphere pressure, because at 25 atmosphere pressure, this mixture condition is no longer an azeotrope. So it has separate bubble point and dew point. So it is possible for you to separate through distillation. So the answer to the query that has been asked in the question, whether change of pressure helps in separation of water acetonitrile azeotrope, the answer is yes, it helps. So our next problem is comparing k-value diagram for butane-heptane binary system using Peng-Robinson and Lee-Kessler-Pöckler equation of state. So for that, again we have to go to the Aspen simulation window. Let us open a new one. So the components are butane and heptane. So we have Peng-Robinson method and Lee-Kessler-Pöckler method. Run those property methods. Okay, they are done. Now we have to bring k-value diagram. And for that, we have to do the binary analysis. So first we are doing with Lee-Kessler-Pöckler. So we cannot directly bring the k-value diagram. First we have to do it with txy. That's what Aspen does. So we run the analysis first with txy, and when it is over, the k-value diagram will be available. So here we are not interested to know about txy diagram. We can bring the k-value diagram from there. So this is the k-value diagram we have. Okay. This is using Peng-Robinson method. Now we have to bring in the second binary analysis tool. Here everything will remain same except the calculation option, which will be Peng-Robinson. So the previous one was Lee-Kessler-Pöckler. This time it will be Peng-Robinson method, and you run the analysis. Yes, it is done. So again, we are not interested in txy plot. Rather, we will bring in the k-values plot. Okay. So we have to distinguish between them. So we write here binary 2. So it will be Peng-Robinson. Okay. And this one is Lee-Kessler-Pöckler. And we have to merge the plot. So we have done. And we have to use single y-axis. Okay. So here we find that we can use only okay, so we use only lines, no marker. Fine. Here we find that the k values are almost same for the entire process except the lower portion of butane. When butane mole fraction is very, very small, then the k values are different for whether you use Peng-Robinson method or Lee-Kessler-Pöckler method. The k values will be different, slightly different, not much. But for higher concentration of butane or heptane, this difference doesn't exist. So our next problem is about methanol toluene binary system. Now, in the past, we have used NIST data set. But suppose if you have your own experimental data, okay, you might have your own experimental data in Excel sheet, Microsoft Excel sheet. So you want to use your own experimental data for regression and some similar purpose. So it is possible for you to feed your own data. Maybe it is isothermal PXY dataset which we have right now in our possession. So I will show you how to feed in some own dataset and perform regression. We can take uniquark model for that. So let us open a new simulation. So this is methanol and toluene. And we have uniquark. Okay. Now, here you have to feed in your own data set, right? Now, I have the data with me in this table. Here, I have an isothermal data set for PXY diagram. So this is my pressure and this is my X in methanol. So I want to feed in this data. So let us say new. It is a mixer. Bring in both of them. And data type, it is PXY. Okay, it is PXY diagram. And the temperature, so as it is PXY diagram, not TPXY, so it is expected that the temperature is fixed. So yes, it is fixed at 313,14006 Kelvin. So all of them are 313,14006 Kelvin. So it is in Kelvin and 313,14006. So I have done at 40 degrees centigrade. So the temperature in Kelvin is 313.14. Now we have to feed in the data. As I have said, it is PXY diagram. So it is expecting the data for pressure, X and Y. So this is the pressure. So just copy and paste. So it is simply, you can use Ctrl+C and Ctrl+V. Okay. Similarly, you choose mole fraction of methanol in liquid phase, Ctrl+C, and here methanol in liquid phase, Ctrl+V. So as soon as you write Ctrl+V over here, the toluene is calculated. Okay. Now at this temperature, 40 degrees centigrade temperature, neither methanol nor toluene will have any vapor phase. So the vapor phase diagram will not be there. Okay. So once this is done, we can check the PXY diagram. So entire thing is my own data. This is the experimental data that I have recorded in my own Excel file that I have copied and pasted. It has not been taken from any data bank like NIST, DKEMA or anywhere like that. It is our own data. So we can press PXY and check. So this is the diagram that we have got. Okay. Pressure in bar and mole fraction of methanol against pressure. So this is the PXY diagram we have to use. Like that, you can copy your Excel file data onto the Aspen Plus domain. So you will get your own data set, and with that you can do the regression or whatever you want to do with the data you can do. So in the problem, we are supposed to perform regression on unique model, but I leave it onto you as a task. You can try it out yourself because you already know how to do the regression. I have already given many examples like that. And the last problem that we have is about generating the PT envelope, pressure temperature envelope, for a mixture containing 24% methane, 15% ethane, 8% propane, 2% N-butane, 2% isobutane, 13% N-pentane, 11% isopentane, and rest hexane. We have to generate a PT envelope and find the bubble and dew points at 25 bar and 50 bar pressures. We have to use SRK, predictive SRK property method. So for that, let us again go to our simulation window, open a new simulation, and here you have to enter methane, ethane, propane, butane, and then we have isobutane also. So isobutane, we search for isobutane and we get this one, and then butane, pentane, and we have to find isopentane, this is the one which we are looking for, 2-methyl-butane, and finally hexane. Okay, so we write it as isobutane and this one as isopentane. Okay, so press next, and we have to use predictive SRK. So PSRK, run the property method. Now we have to bring in the PT envelope. This is the generate PT envelope. Bring in this tool, and we have to give some flow rate. So it is in the molar percent, we already have the data, 24% methane, 15% ethane, 8% propane. So we can write 24, then 15, then 8, and butane 2%, 2%, 13, 11. So 2, 2, 13, 11, and rest is hexane. So hexane becomes 24 plus 15 plus 8 plus 2 plus 2 plus 13 plus 11. So it takes total, it is 75. So it remains 25. So 25 hexane. Okay. And yeah, so everything is set. So you can run the analysis. So this is the PT envelope that we have got. The green line is the bubble point line and blue line is the dew point line, because here the temperature is higher. This is the pressure. So we are asked to find out the bubble and dew points at 25 bar and 50 bar pressure. So we have to check over here. It is 20 bar and 50 bar. These are the 2 points. So we just bring one line over like this. So this is the line we draw, and this is another line we draw, and this is the points that we are looking for. Okay, so at 20 bar pressure, the dew point of the mixture is 135 or 36 degrees centigrade, and the bubble point will be minus 65 to 68 degrees centigrade. And at 50 bar pressure, the same thing will be 175 and nearly 0 degree, maybe 1 or 2 degree centigrade respectively. So that's how you find out the dew point and bubble point from PT envelope. Obviously this entire thing will be liquid over here, and this will be the vapor phase, and this entire thing, this is liquid plus vapor region. Okay, so that's how we find the PT envelope. So we end our problems for binary mixture. So with this, we end our lecture today. At this point, we'll continue in the next lecture. Thank you.